Hello and welcome back to another IB Math speedrun with me, Vince. In this speedrun, we're going to be going through chapter 10.3 of the IB Math textbook, which is all about powers and roots of complex numbers in polar form. So let's jump right in. So one of the other things that's much easier to do than with complex numbers in polar form than in Cartesian form is powers, because if you think about it, if you have a complex number z is equal to e to the r e to the I theta, well, z to the n is just equal to r to the n e to the I n theta. And so similarly, since this is equal to r cis theta, z to the n is equal to r to the n cis n theta. So yeah, that's pretty much all we need to know. Oh no, my screen. There. That's pretty much all we need to know, so now we can jump into some questions. So the first question is, given the numbers z1 is equal to 1 plus I, and z2 is equal to 2e to the I 2 pi over 3, we need to find z1 cubed times z2 squared. So let's find this first. It will be much easier to convert this into exponential form, though. So we have tan theta is equal to 1, theta is equal to pi over 4. So this is equal to square root 2 e to the I pi over 4. Okay, now that we've got that out of the way, we can now we can now do our equation. So z1 cubed times z2 squared is equal to, well, 2 root 2 e to the I 3 pi over 4 times 4 e to the I 4 pi over 3, which is equal to 8 square root 2 e to the I 3 pi over 4 plus 4 pi over 3 is 25 pi over 12. So this is the new one, which is also just equivalent to pi over 12. So notice, of course, if we square complex numbers, they just rotate around the origin. Yeah. Okay, so that was that. And the next one we need to do is we need to get z1 to the power 4, the conjugate of z1 to the power 4, times z2, the conjugate of z to the 2 to the power 5. And just remember that the conjugate is equal to pi minus the angle with the same modulus. Okay. So we have z1 to the 4, so we need to get the modulus of, this is just 4 e to the I pi, which is funny because that's just negative 4, but we'll convert that later. We're multiplying it by the conjugate of this, so this would be 2e to the I pi over 3 to the power of 5. So 4e to the I pi is negative 4, so the conjugate is negative 4 still. Oh, sorry, we're mirroring it. Sorry, I forgot. Conjugates we have to mirror, so that's actually going to be the negative value of pi. Anyways, so this is actually negative 2 pi over 3. So 4e to the I pi, negative 4, conjugate negative 4. So we have negative 4 times 2e to the I, whatever that will be. So let's get that. So 2 to the 5 is 32. E to the negative I 10 pi over 3 times negative 4. So since this is negative, remember we flip around the sign over here, so we actually end up with 128 e to the I 10 pi over 3. Is that correct? Ooh, no, I've messed it up somewhere. Sorry about that. I don't understand. The book says it's supposed to be 64, but I've got 128, and I think 128 is correct, not 64. So anyways, let's move on to the next question. where we are given z1 is equal to square root 2 CIS pi over 3. Is that equal to CIS pi over 3? Yeah, I'll just write out the full thing. So z1 is equal to square root 2 times cosine pi over 3 minus cosine 5 pi over 6 I, and z2 is equal to 2 times sine 5 pi over 6 minus sine pi over 3 I. We need to find z1 cubed over z2 to the 5. Okay. So what we know, we need to convert this cosine 5 pi over 6 into a sine value. And luckily, cosine minus cosine 5 pi over 6 is equal to plus sine pi over 3. Yeah. So we can rewrite this as square root 2 CIS pi over 3. And then here, sine 5 pi over 6 is 1/2 minus sine pi over 3. Oh, I got it. This can be 2 CIS negative pi over 3. Since this is equivalent to 0.5 minus square root 3 over 2. So 1/2 minus square root 3 over 2, which is negative pi over 3 I. So if we need to find z1 cubed over z2 to the 5, that's going to be equal to 2 square root 2 CIS pi divided by 32 CIS negative 5 pi over 3. So if we're dividing these two, this is equal to square root 2 over 16 CIS pi plus 5 pi over 3 is equal to 8 pi over 3, I think. So is that the answer? Okay, so they want us to convert this. 8 pi over 3 is equal to 2 pi over 3. So they want us to convert this back into Cartesian form. That's okay. So this is square root 2 over 16 times cosine 2 pi over 3 is equal to negative root 3 over 2. Cosine 2 pi, no, this is just negative 1/2. Sorry. This is just negative 1/2 plus root 3 over 2. So this is equal to square root 2 over 32 negative square root 2 over 32 plus square root 6 over 32 I. So yeah, that was cool, and then we can move on to the next one. And the next one is we have a geometric sequence of complex numbers is 2 plus I, 1 plus 3i, negative 2 plus 4i, and so on. So we need to find the common ratio. Find the common ratio. Next, what is the 9th term? And find the sum of the first 9 terms. Okay, so we know that 1 plus 3i over 2 plus i is equal to negative 2 plus 4i over over 1 plus 3i. Well, I mean, since it's a geometric sequence, we can just use that to verify it later, but more or less, we need to calculate what this is. So, of course, we could solve this Cartesianally, but I kind of want to convert this into a geometric form. So can we convert each of these terms into a geometric form? So we have tan theta is equal to 1/2. So theta is equal to Actually, maybe not. Maybe let's just solve this Cartesianally. So we have 1 plus 3i is equal to a plus bi times 2 plus I. So we have 1 is equal to 2a minus b, and then 3 is equal to 2b plus a. So of course b is equal to 2a minus 1. So 3 is equal to 2 times 2a minus 1 plus a, which is equal to 5a minus 2. So a is equal to 1. And b is equal to 2a minus 1. So that's b is also equal to 1. So we have 1 plus I as the common ratio. So the common ratio is 1 plus I, but maybe we could express that in Euler's form, which is equal to square root 2 times e to the I pi over 4. Next, what is the ninth term of the sequence? So the ninth term of the sequence is equal to 2 plus I times square root 2 e to the I pi over 4 to the 8, which is equal to 2 plus I times 16 e to the I 2 pi, which is just 16. So the ninth term is equal to 16 times 2, 32 plus 16i. And then find the sum of the first 9 terms. So this is going to be equal to, what is this? Is it the first term times 1 minus r to the n over 1 minus r? I'm pretty sure it is this. Oh, sorry, it's r to the n inside the brackets. Okay. So this is equal to, well, the first term is 2 plus I times 1 minus r to the n. So 1 minus 2ei to the 8. I'm pretty sure this is n minus 1. This should be n minus 1. Yeah. So we already have that value. That is 16 e to the 2i. So this is 1 minus 16, or negative 15, divided by 1 minus r. So that r, the common ratio is 1 plus I, so that's just negative I. So this is equal to, let's just divide these two first. So we have 2 plus I is equal to negative I, a plus bi times negative I. So 2 is equal to b, and a is equal to negative 1. So this is negative 1 plus 2i times 15. Is that it? Hold on, I think something's wrong. A1, so the first term, times 1 to the n over 1 minus r. The common ratio is 1 plus I, 1 minus r to the n. Oh, maybe it is 1 to the 9 actually. I think it might actually be 1 to the 9. Me being silly. Okay. So that's equal to 1 plus I, oh sorry, no, what is it? 2 plus I times 1 minus 16 times 16 square root 2 e to the I pi over 4, which is 16 times 1 plus I, divided by negative I. So we have 2 plus I times 1 minus 16, so this is negative 15, minus 16I, all over negative I. So if we multiply this top part out, we get negative 30 minus 32I minus 15I plus 32 all over I, negative I. I think that's correct. Sorry about that. I just realized I was being silly. I accidentally multiplied negative 69 by 2 instead of just 1. So this should only be for 16. So this is going to be 14 minus 47 over negative I. So therefore this is equal to 40 minus 47I over negative I, which is equal to A is equal to negative 14, B is equal to 47. So we have that the sum of the geometric sequence was equal to 47 minus 14I. So that was all for the speedrun. I hope you enjoyed it, and I hope to see you in the next one. See you then.